It's my pleasure to introduce Daniel Duarte, Professor Daniel Duarte, from ConacyT and also from Universidade Autônoma de Zacatecas. He's going to talk about Nash blowups and positive characteristics.
Sí. Okay, well, thank you for the introduction. And thanks to the organizers for the opportunity to talk here. It's an honor to be and to talk here, so thank you. And thank you all for being here in this the very last talk of the Congress. And since it is the last one, maybe we can thank the organizers for all of their work. So thanks. Okay, so this talk is about Nash blowups of algebraic varieties defined over fields of positive characteristic. Okay? The main result that I want to discuss is a criterion of non-singularity of algebraic varieties using these Nash blowups. Okay? So these blowups were already defined by Enrique, by Nivaldo, but well, I'm going to define them again. Okay? So the definition is the following. Okay? Throughout this talk, X will always denote an irreducible algebraic variety of dimension D. And I always assume that the field is algebraically closed of any characteristic. Okay, so to this variety, we can consider the Gauss map, which sends which sends any non-singular point to its tangent space. Okay, this is well defined because we are taking only non-singular points, and this is irreducible. So we consider the graph of this map, the graph of G. Okay, this is inside X times the Grassmannian, ds. Okay, so here we have couples of the form a non-singular point and its tangent space. Okay, so to recover singular points, we take the closure. We denote this as X star. Here we have a projection to the first entry. And I denote as pi the restriction to this variety. Okay, so X star with this map is the Nash blowup of X. Okay, so in this modification, in this variety, singular points are replaced by construction, are replaced by limits of tangent spaces, okay, at this point. Okay? So since we are modifying the singular locus, it is natural to ask whether this construction gives a resolution of singularities. Okay? So the first question that appeared related to Nash blowups is whether if I start with some singular variety, I do the Nash blowup. This usually has singularities again, so I repeat the process. Okay? So the question is whether this solves singularities. Okay? This is a question that is usually attributed to John Nash, but it also appears in the work of Semple, okay? Some years before Nash. Okay, so there are some partial results on this question. It is known that it's true for some families of varieties, but so far I think that probably the most general result so far is a theorem due to Mark Spivakovsky from the 80s. Spivakovsky, okay. And then from the 85, okay, which says that normalized Nash blowups solves complex surfaces. Okay, So, okay, this is a theorem from the 80s. And this is over the in-characteristic 0, okay? Now, in positive characteristic, the story is quite different. Okay, let me compute an example. Okay, example. Okay, assume, let us consider the cusp, okay, x3 minus y2 in K2. But now we assume that the characteristic of the field is 2, okay? So let us compute the Nash blowup. Okay, so by definition, this is the couple's point on the curve and the tangent space, which in this case is given by the partial derivatives, right? 3x squared minus 2y. Okay, and the point should be not singular, so this is not the origin. Okay, and the closure. This is just the definition. Okay, now we are in characteristic 2, so this one is actually 0. Okay, so this element in the projective space, we can write it just as 1, 0. Okay, so in this coordinate we have a constant coordinate. So when we take the closure, this doesn't change. Okay, so we can identify this with x, y in the curve, such that this is not the origin, and then we take the closure, right? This is the curve itself. Okay, so this is like very bad news, right? In positive characteristic, you start with the simplest curve singularity. You do this process of Nash blowups and limits and all that, and you obtain exactly the same curve, okay? Well, so in particular, forget about solving singularities using Nash blowups in positive characteristic, okay? So one of the first results that appeared in the theory of Nash blowups is due to Nobile, Augusto Nobile, in 75. And he says that, or the theorem states that, this phenomenon, it doesn't happen in characteristic 0, okay? Let characteristic of the field be 0, okay? If it happens that the Nash blowup is isomorphic to the original variety, it is because the variety was already non-singular, okay? X is non-singular, okay? This is the theorem by Nobile. Okay, so of course, in positive characteristic, it is false, okay? So what this theorem says is that, okay, another way of explaining this theorem is that if you start with a singular variety, then the Nash blowup does something to the variety, okay? We don't know, it changes the variety, okay? We don't know if it changes, if the change is good or bad, but it changes. So you can actually try to answer this question, okay? Because the Nash blowup is doing something to the variety, okay? In characteristic 0, okay? So the thing is that, okay, because of this example, the community interested in the theory of Nash blowups, well, essentially abandoned the theory in positive characteristic. And it is reasonable. Oh, what's the point? You want to solve singularities, and the simplest one cannot be solved, so what's the point, okay? So what we are doing, together with Luis Núñez from CIMAT, is our result is an attempt to bring back to life Nash blowups in positive characteristic, okay? The thing is that, okay, we don't have a Nobile's theorem for arbitrary characteristic, it is false, but adding an extra condition gives us a Nobile theorem in any characteristic, okay? So the theorem says, Okay, now let the characteristic of the field be positive and assume that the variety is normal. Assume that X is normal. Okay? Then same statement. Okay? X star isomorphic to X implies X non-singular. Okay? So this is the result. Okay? So now we have the same interpretation. Okay? If we start with a normal variety and we do the Nash blowup in arbitrary characteristic, something is changing. And once again, our proof doesn't say if it changes for good or for bad, but something's changing. So we can reconsider the original question. But we have to do the Nash blowup and then normalize. Because usually the normal condition is not preserved when we do the Nash blowup. Okay, so we have to do the Nash blowup and then normalize, exactly like in Spivakowski's theorem. Okay. Okay. So in the rest of the talk, I want to explain the motivation to study Nash blowups in positive characteristic, and also to explain why or how the normality condition appeared. Okay. So this is what follows in the talk. Okay. Now, the story goes as follows. Nobile's proof of Nobile's theorem is analytical. Okay? He works over C, and then he uses complex algebraic, complex analytical geometry, tools from complex variables. Okay? And at the end of the paper, he suggests that maybe an algebraic proof could throw some light on the question, right? An algebraic proof. Maybe motivated by this, Bernard Tessier gave a proof of Nobile's theorem, an algebraic proof. Okay? Now, and there's where our motivation lies. But to explain Tessier's proof, I need to give a more general definition of the Nash blowup. Okay? One that does not depend on the embedding of the variety on an affine space. Okay? So the definition is the following. Okay, now X will be, okay, this is a completely general definition. Now X will be an Noetherian irreducible scheme. Okay. Now, to this scheme, Grothendieck constructed the so-called Grassmannian of locally free quotients of omega 1 of rank D. Okay? This is an X scheme, okay, having the property that the pre-image of points here can be identified with the usual Grassmannian of the dimensional subspaces of the tangent space at that point. Okay? This is an important property of this X scheme. Okay? Now, the property that we need to define Nash blowups and for Tessier proof is the following. Given any morphism here, okay, it is equivalent that the pullback of omega 1 has a locally free quotient of rank D. Okay, this fact is equivalent to the existence of a map here, making this diagram commutative. Okay? This is the important property for us. Okay? If the modulo of differentials, when you take the pullback and it has a quotient with these properties, then there exists this map. Okay? Now let us apply this universal property to the set of non-singular points. Okay, let me call U X without the singular points. Here we have the inclusion. Okay, here we have the Grassmannian, omega 1. But we know that I star of omega 1 of x, which is simply omega 1 of x restricted to the set of non-singular points, is locally free. You don't need to take any quotient. This sheaf is already locally free, okay? Is locally free. Okay, so by the universal property, there exists a map here, okay? And so the Nash blowup, okay, in this context is the image of this map, and then we take the closure. Again, we can take the map, and pi is the restriction to this set. Okay, so this couple is the Nash blowup. Nash blowup of x. Okay? It is an exercise to show that using this property, that in the affine case, the definition I gave before with the limits of tangent spaces is the same as this one. Okay? Okay. So this is the definition that Tessier uses for his proof. Okay? Now let me give you the global idea of Tessier, no? for Nobile's theorem. Okay? Okay. Tessier's proof. Once again, universal property. Assume that x star is isomorphic to x. Okay? So we have the following diagram. Here we have the Nash blowup. Okay? Here we have the, since it is an isomorphism, there exists the inverse. Okay? Here you have the identity, and so this diagram commutes. If the diagram commutes, means that the identity, the pullback under the identity has a locally free quotient. Okay? So by the universal property, the pullback of the identity, which is omega 1, has a locally free quotient of rank D. In other words, there exists a locally free module, and this surjective morphism. Okay, this one is locally free. Okay, so what's next? We want to prove that x is non-singular. Okay, so this is we're going to do this point looking at each point. Okay, so we fix a point in x. We call R the local ring, and we want to prove that this ring is regular. Okay, so because of this, okay, we can localize at x to obtain the following surjective morphism. This is locally free. Okay, so this one is R to the D. Okay, and this is surjective. Okay, now consider any projection to R. See, the first projection, for instance. Here you have the universal derivation. Okay, and we know that. Sorry. Well, I don't know. You know what I mean. Okay, this derivation. Okay, and we know from commutative algebra that this composition is a derivation. Okay, it's a linear map that satisfies Leibniz rule. In addition, the fact that these two are surjective. And the fact that the image of this one generates this module implies that the image of the ring is not contained in the maximal ideal. Okay? It's a computation from these facts. And then notice that up to this point, I haven't said anything about the characteristic. Everything is free of characteristic up to this point. Okay? Then the characteristic is just at this moment. With these conditions, there is papers and results of Zariski, which are valid only in characteristic 0. Okay? That says, with this condition, okay, there exists a subring of the completion of R and some element in R, completion, such that this one is R0, okay, and the dimension of R0 is dimension of R minus 1. And this allows Tessier to do induction on the dimension. Okay? When the dimension is 0, you have a local, reduced, zero-dimensional ring. This is a field, which is regular. Okay? So the key part of Tessier's proof is this result by Zariski. Okay? The existence of this subring and all. Okay? This is constructed, actually, is explicitly constructed, this R0. Okay? So the only moment where the characteristic is used is right here, at the very end of the proof. Okay? So we want to provide a proof that does not, which is valid also in positive characteristics. So this, so we cannot go in this direction. Okay? This is false in, well, yeah, it's false in characteristic, in positive characteristic. Okay? So now, let me take Tessier approach in a slightly different direction. Okay? Okay, so let us take advantage that up to this point, everything is free of characteristic. Okay? So Tessier shows, using this universal property, that this isomorphism for each point of the variety, there exists a surjective morphism to R to the D. Okay? That's like the second step in Tessier's proof. Okay? Now, this one is a free module. Okay? So, surjective morphism, this one splits. Okay? You can take to any generator, any element of the basis, take any preimage, and you have this splitting. Therefore, omega 1 of R is isomorphic to R to the D, direct sum with some submodule. Now, this R to the D is the largest free submodule that this one can have. Okay? Therefore, this one is contained in the torsion submodule. Omega 1 of R. Okay? So now we're going somewhere, okay? Because I guess that now you are seeing that if this one is not there, omega 1 of R is a free module of rank D. The usual criterion of regularity using omega 1 says that R is regular. Okay? So we have to get rid of this distortion. Okay? And this seems like a familiar object, like an exercise in Matsumura's book. Huh? This is like no, it seems like an elementary question. How is the torsion of omega 1 of a finitely generated K algebra, for instance? No? So Luis and I went to the literature, and there was a theorem. We found the following theorem. Okay? This is due to Liebman, and independently to Satoshi Suzuki from '64, which says that under these conditions, no, more, a little more. Let me go back to the affine case. X complete intersection. Okay? For a complete intersection, it is equivalent, I'm sorry, with the same notation as before, OXX for some point in X. It is equivalent that the torsion of omega 1 is 0 to R being normal, of course. Okay? So that's it, right? Notice that putting together Tessier, first part of Tessier proof, and the result of Liebman and Suzuki. So what am I saying? If we have an isomorphism for a complete intersection which is normal, okay, then, okay, as before, R is OXX, then omega 1 is isomorphic to R to the D, which implies R regular. Okay? So it's very nice. I mean, like more than 40 years ago, the theorem of Nash blowup Nobile's theorem in positive characteristic was already proved. No? These are okay, from the 60s. Okay? So this is where the normality condition appeared for the first time in our approach, in our study of this problem. Okay? Of course, if you remove this hypothesis, this is no longer true. Okay? You may have non-complete intersections which are normal and having torsion. Okay? So we needed to look for another way of getting rid of this part, right? Okay? In the general case, of course. So after this, we tried some other families like normal toric varieties, F-pure varieties, quotient varieties, and always the normal condition was helpful all the time. So we decided to consider the general case, to try the general case. And now, notice that all this is free of characteristic, right? Everything I said here, this theorem is free of characteristic, okay? Maybe it is too ambitious to pretend to have a proof of our theorem which is free of characteristic. Maybe that's too much. So we moved to the positive characteristic case. There are specific tools in this context, no? which can be used. And of course, Frobenius morphism, for example. Okay? So now, let me explain how the proof of our theorem starts. Okay? Okay. Okay, so from now on, we assume that the characteristic of the field is P greater than 0. We assume that X is isomorphic to the Nash blowup, that X is normal, X normal, okay, all the hypotheses. And let me call R a local ring of a point of X. And I want to prove that R is regular. Okay, so Frobenius morphism. Okay, I'm going to consider the ring of pth roots of elements of R. Okay, these are the pth roots of elements of R. We look for these roots in an algebraic closure of the field of fractions of R. Okay? Okay? Okay, this is the object that we have to study. Okay? R is contained here. Okay, because any element F here is the pth root of F to the P. So this one is here, making this one an R module. Okay? Now, notice that the last step here was this criterion of regularity using omega 1. Okay? The corresponding statement in positive characteristic is the famous theorem of Kunz, which says R is regular if and only if this one is free as R module. Is a free R module. Okay? And here the expected rank is, there was D, the rank was D. Here the expected rank is P to the D. Okay? So nobody proves the non-singularity directly from the definition, right? You look for some characterizations of regularity. So now the proof will try to prove that this one is free, okay, of this rank. Okay? Now, to do that, okay, what's the next? Okay, again, by TCM, we have that the free rank of omega 1, okay, the largest rank of a submodule of omega 1 is D. Okay, that's what I said over there. Okay, and here, okay, so we need to find P to the D copies of R, okay, and make it isomorphic to this one. Okay, so let me start with the D. Okay, so this one is from TCM, okay, but in a recent paper by Olger Brenner, Jack Jeffries, and Luis Núñez Betancourt, this is from last year, they proved that this one is equal to the dimension of K as K vector space of M over, not this one, no? No, this is not true, right? Well, I mean in general. But here, if you put the second differential power, then this is true, okay? Actually, they proved something much more general. Here, they write the module of principal parts, and here they have R over M plus 1, okay? I only need this one, so that's why I stated this one. Okay, so from here, we already have the distinguished elements, okay? I'm going to take the elements from here in a moment, okay? Notice that I already erased it, no, it's here. This derivation was key to Tessier's proof of Nobile's theorem, right? Because of this and this induction, okay? So we're going to look for some derivations in this context, okay, also. And they come from, I'm sorry, I didn't say what is this. Okay, this one is the elements in R which are sent to the maximal ideal for every derivation. Okay? In addition to this one, I need an extra submodule, which is the derivations of R sending all of R to M. Okay? M, 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 okay? M, okay? Notice the resemblance of the arguments, okay? Now, with all this notation and objects, these guys also defined the following bilinear form. The derivations of R modulo J1 times M times this second differential power to R over M, sending the class of a derivation, the class of an element, to the class of the image of that class, okay? So they proved, also actually in a more general situation, that this is a non-degenerate bilinear form, okay? So we already know that this one has dimension D using the non-degeneracy. Okay. Brenner, Jeffries, Núñez Betancourt is a non-degenerate bilinear form. Okay? Okay, so because of these remarks, this part of the board, hence, okay, there exist elements in the maximal ideal and derivations in the derivations of R such that these derivations on these elements is a unit if and only if I equal J. Okay? Okay, from everything I said here, this is a consequence. And now, okay, so remember, I'm looking for P to the D copies of R. So the copies are the following. Let me call A, no, sorry, I'm going to define this directly. With alpha in N to the D, 0 greater or equal than alpha I less than P. Okay, so here we have P to the D copies of R. And I'm going to send each basis element to these elements, x1, alpha 1, xd, alpha d, and then we take the pth root of this element. Okay? The claim is, okay, this one is an isomorphism. Okay? So, so this is how the proof starts. Okay? Now to prove that it is an isomorphism, we actually find the inverse. Okay? And to do that, we use, of course, these derivations that appear here, okay? Because the matrix formed by with these entries is invertible, so you take the inverse, and then you start to construct the inverse, okay? And I think I still have 1 minute, so maybe I can comment very fast how the normality is used, because up to this point, and the normality, where is it, right? The normality is used in two key elements. It is more like an auxiliary tool. It seems that it is not essential, no? But it is helpful for the proof. Okay? To prove that this map, for example, to prove that this map is an isomorphism, it is enough to show that when you localize at any prime ideal of height 1, then the corresponding map is an isomorphism. Okay? CQ is an isomorphism for all Q of height 1. Okay? So instead of working with this map directly, we localize at primes of height 1. Okay? If you have this, if you can prove this, then you have the claim. Part of the proof also uses the usual result that RQ is regular. Okay? RQ is regular for all Q with this condition. Okay? Normality implies regularity in codimension 1. Okay? So, since this is regular, by Kuhn's theorem, we obtain some free module. Combining that free module with these derivations, these matrices, this matrix, we construct the inverse. Okay? So here there are details. Okay? And that's the idea, and that's it. Thank you.